Hey guys, and welcome to Chapter 2, Summarizing and Graphing Data. Um, Hopefully some of the stuff on the screen will go away as we start. So let's get going. So the first way we're going to talk about graphing data is using a frequency distribution. This is kind of one of the best tools when dealing with large sets of data to organize and kind of see what your data looks like. And this is typically done when we have large numerical data sets. Those data sets could be things like ages, they could be measurements, they could be observations, it could be a lot of different things. Um, if you have more kind of categorical data, like genders, say preference on makers of cars or things like that, those would typically be displayed in other ways, and we'll talk about those in a little bit. So frequency distribution tables are a way that we can represent large sets of data, okay, by listing all the categories along with the number or frequency of data values in each of them. Okay, so as I just said, right, these are used for large sets of data. We can analyze kind of the nature, the shape is typically the word we use, the shape of the data. And then from this, we can build further graphs that kind of allow us to see some even more telling features. So what we're going to do is, instead of kind of giving you these like basic ideas, we're going to run with this example data set here. This is already a frequency table that's been created based on a observation or a recording of IQ scores of a population of people. And so these IQ scores we can see kind of have a wide range. We can see kind of where they lie. So let's kind of break it down, this frequency table, a little bit further. Okay. So the first thing we notice, or maybe not the first thing we notice, but the first thing that we're going to talk about is something called a lower class limit. A lower class limit is the smallest number that can actually belong in the different classes. So let's go to my pointer. All right, yeah, nice. So we can see that these numbers here create our different classes. Now, depending on what type of data you have, if you have discrete or continuous data, these kind of limits, these edges may be a little different. Because if you had continuous data, obviously this wouldn't go from to 69, and then this wouldn't start at 70 because that eliminates everything between 69 and 70, 69.5, 69.5431, all sorts of stuff like that. So if we had that sort of a situation, what we would say is this would be something like 70 with kind of an open-ended interval. We would use some maybe inequality or interval notation to represent that going on here. But for this case here, IQ scores are a discrete type of data. You either are 59 or 58. There's no in between. Okay. So the lower class limit, we can see here, is the smallest value that can possibly fit. So we know that there's one person who has a minimum IQ score of 130. The upper class limit is very similar, right? We can see those here. And that is simply the largest number that can actually belong to the different classes. So kind of using this thing here, we know there's one person who has a maximum IQ of 149. There's no one in this data set that has an IQ of 150 because that's not in this group here. So upper class limit, lower class limit are what define our classes or categories or groupings, and those are really easy to calculate. We're going to talk about how to figure those out in a little bit when we talk about how to create this chart. Okay. Class boundaries. So these are typically numbers. This is kind of getting at kind of the idea of continuous values, but it's kind of using these kind of half a digit. So let's say we were talking shoe sizes. So here we've got whole numbered values. So then our cutoffs are kind of a half below those lower limits and above, or in the upper limits, kind of halfway between the upper limit of one class and the lower limit of the next. So 129 to 130 means we have a class boundary of 129.5. Now, if we were talking about shoe sizes for some reason, right, so then our values aren't whole values, but there's halves, in which case our jump would be maybe from 8.5 to 9. So then our class boundary would be 8.75. It's just kind of halfway between the upper limit of one class and the lower limit of the next class. Okay. Honestly, class boundaries, not really something we're going to utilize in this class. Lower limits, upper limits, definitely going to use these a lot. Okay. Midpoints are the other thing we're going to use a lot in this class, okay? Using class midpoints are the way we kind of approximate the data values in that category. So the way we find it is very simple, okay? We add the lower limit to the upper limit and divide by 2. We're finding the mathematical average or the arithmetic average of our class limits. So if we take 50 plus 69 and divide by 2, we get 59.5. And so the way that works, and we'll talk about this more in chapter 3 when we talk about finding averages, the way that works is we can use this. So the problem with a frequency table is I don't know what these two IQs are. I just know they fall in between 50 and 69. And so we can approximate some information from this table by assigning these two frequencies to 59.5. In other words, assuming they are the average value in here, kind of hoping that they kind of balance each other out, which isn't necessarily true, but it is something that we kind of work under the assumption of. And that's why when we do something like that, we would definitely say that that is an assumption or an approximate value. So class midpoints are another one. Again, really easy. Lower limit, upper limit, divide by 2. Class width. This is the basis of what we build these tables off of. We have two kind of real key things that we need to build these, and that is the number of classes you want and then the subsequent class width. Okay. Now notice the class width is 20. It is not the distance from here to here, but it is the distance between any two consecutive lower limits or upper limits, or really any singular characteristic. So the lower limit 50 to the lower limit 70, that has a difference of 20, 20, 20, 20. So our class width is 20. If we think the same thing with the upper limits, 69, 89, 109, 129, 149, those also have a class width of 20, all the same. If you even go to the midpoints, 59, 79, 99, 119, 139, again, width of 20, okay? Class boundaries, all of those values have a class width of 20 because this data table, this frequency table, has a class width of 20. So let's talk about, let's just pull all these up. Let's talk about how we build this, okay? When we're building a frequency table or a frequency distribution, as you will often see, the first thing we need to figure out is how many classes we want to have. Now, this is not some mathematical formulaic thing that you have to figure out. It's simply based on the data and kind of what you're seeing. If your data is very widely spread over a very large range, you may want to have a couple more classes so you can kind of capture some things that are happening. And honestly, in a real experiment, if you were doing this with some raw data that you'd collected for something, you might play around with this and choose, okay, well, let me try 6 classes. Let me try 15 classes and just kind of see which one kind of gives you the simplest and yet most informational picture of your data, okay? For the purpose of this class, as far as any questions I'll be giving you, I will tell you the number of classes you need to have. So I'll say something like create a frequency distribution for the data given 5 classes, okay? So then you use that to fill in the rest of this. So once we have our number of classes figured out, then we need to figure out our class width. And it's really simple, okay? We're going to take the maximum value in our data set. We're going to subtract the minimum value in our data set. We're going to find that difference between the max and minimum value. And then we're going to take that number and we are going to divide by the number of classes, okay? That is what we are going to do, okay? Take the max value, subtract the minimum value, divide by the number of classes. Now, division is not always perfect. Sometimes we get partial values. We may divide and get something like 7.5, 7.1, 7.3, 7.9. All of those values, 7.1, 7.3, 7.5, 7.9, all of those will be rounded up to have a class width of 8. So it doesn't matter if it's just over it by just a little bit. Okay, if it's 7.025, we're going to round that up to a class width of 8. And the reason why is if we round down, our classes won't be wide enough to encapsulate all the way from the maximum or from the minimum value all the way up to the maximum value. What will end up happening is that maximum value will actually end up outside of our last class. So we have to make sure we always round up. Okay. So we've figured out our number of classes, or we were given our number of classes. We've calculated the class width. The next step is to choose a starting point. Okay. So what this is doing, if we go back to the example table, it is choosing that lower limit of our first class. Okay. So once we've chosen that lower limit for the first class, it's really easy. We know our class width, so we can use that first limit and give us all of the subsequent lower limits. So coming back here, if I were creating this table for myself, once I found out that I needed a class width of 20, and I want my first lower limit to be 50, I would go and list out 50, then I'd add 20, 70, add 20, add 20, add 20 to get all my classes. Okay. Once we have all of our lower limits, okay, then we would use that to find our upper limits. Okay. As you can see here, proceed to enter the class upper limits. To do that, you just simply take whatever this lower limit of the next class is and subtract 1 for the upper limit of the previous class. And again, this is with kind of discrete data that jumps from whole number to whole number. Okay, depending on what your data looks like, you may need to jump differently. But for the purpose of this class, we are going to pretty much always be using discrete whole number data. So you would jump from, say, 70, you'd go back 1 to 69, just like we do here. Okay. Then, last thing, you're going to take each individual data value and put a tally mark in the appropriate class, or count them up. There's lots of ways you can do this. Ultimately, what you want to end up with is a count of the number of frequencies, or the number of different times a data value occurred that fell within this class. So if we had a list of all the data values here, we would go through and count up all the ones that occurred between 50 and 69. We'd find that there was 2, so we'd put a 2 here. You can use tick marks and then put a total. What I personally like to do is I like to put a little mark above the number in the list of data. That way, not only do I kind of keep track of how many I'm counting, but also I can see which data values I have utilized and created my table already. Okay. Awesome. So if you have any questions about this, email me. This is something that you're definitely going to be asked to do on a test 100%. I can guarantee you will be asked to fill this in. Okay. The next thing we're going to talk about is a relative frequency distribution, or a relative frequency table. Okay. This is very similar to a frequency distribution or a frequency table. The classes are the same, the class limits and the width and the midpoints and all of those things, the upper and lower limits are the exact same as they were for the frequency distribution. The difference is that instead of putting a physical count or a frequency, we are going to figure out a percentage or proportion of the total data values that occurred in that class. And to do that, it's really easy. To find the relative frequency, you're going to take the frequency in that class and divide by the sum of all frequencies, or the total number of data points. So if we come back here, okay, and we want to do a relative frequency table for this. Okay, let's do one more interesting. Let's do this second class here, 70 to 89. Okay, there are 33 total frequencies in here. So we're going to take 33 and we're going to divide that by the total number of data values. The way we can find that is simply adding all of these up, okay? And when we do that, okay, when I take 33 divided by when we take 33 divided by that total, we get 0.423, okay? And that gives us our relative frequency. If we want to make that a percentage, right, you simply just multiply that by 100%, okay? And we can see here that we just tack on another column to the frequency distribution, and we get this relative frequency distribution, or this relative frequency table. Now, if you want to create a table where you have both of these, that's great. It makes it nice so you don't lose any information, but typically you'll see with one or the other, not both. Okay. Now, there are some benefits to using frequencies or relative frequencies and vice versa. Okay. One of the nice things about using frequencies is you're able to calculate the total number of data values used. We know exactly how many data values are used. We don't know that with relative frequency. But with relative frequency, we have a better idea of kind of what percentage or what proportion of that data fell into that category. So here we see that there is one person with an IQ between 130 and 149, right? One person be like, well, that might not be bad, but that's only 1.3% of our data. So kind of having that kind of overall holistic idea is really nice with relative frequency. Cumulative frequency distribution. It's really rare that we ever use this. It's something that exists, but it's just not something we use. Basically, what it's doing is it's kind of tallying up kind of the total from that class and all the classes below. So the first one, there's still 2. The next one, it's 35 because we have 2 here and 33 here. Then it goes up to 70 because we had 35 in the first 2 classes and then 35 new ones. And then we go up 7 more, so we get 77. Up 1 more, we get 78. So not really used very often, not super helpful, not very good at kind of showing us what's happening with the data, especially if you kind of eliminate this column and just see this information. It's not very helpful. Gaps. Now, that is something that is a very interesting result. It's not something that happens all of the time, but it is something that can happen. And there's a really cool example we're going to talk about in just a minute where it shows a very clear gap happening. What's really nice is when you just look at a data set of numbers, it's really hard to see that. But when you look at a frequency table, it makes it really easy to see. So let's look at an example of where this happened. Okay. On the next slide, we're going to talk about this, where they took the weight of randomly selected pennies. Okay. And they weighed these in grams. Now, the thing is before 1983, as it says, before 1983, pennies were made up of 95% copper and 5% zinc. After 1983, they were only made of 2.5% copper and 97.5% zinc. Now, copper and zinc do not weigh the same. They can have the same kind of mass or size, but they will weigh different amounts. And so because of that, we get this gap. We have a group of pennies that weighed here and a group of pennies that weighed out down here. And so that right there can be caused by a natural variation in whatever it is that you're studying. In this case, pennies. One group is pre-83 pennies, one group is post-83 pennies. I don't know which group is which, but if someone is more inclined with chemistry and weight and everything like that, let me know. Histograms. Histograms are another way to represent data. Again, this is something that's very similar to a frequency table. It's something that we will typically create a frequency table and then create the subsequent histogram based off of that because it makes it really easy. Okay. Our histogram is equal width bars that are not adjacent to each other. They're next to each other, next side by side. There's no kind of gaps between the bars. Okay. If there's a gap between the bars, we assume that there's a gap in the data, such as with the pennies. Okay. In a histogram, our horizontal scale or our X scale is the classes, and our vertical scale is the frequencies or relative frequencies. Okay. And the heights of those bars are kind of how frequent those values were. So if we look here, here's our frequency table for our IQ scores. Okay. And then this is our histogram for those same IQ scores. Now there's a couple of things I want to point out, and notice that what they used for the limits of these bars were not the same limits as the classes, but they used the class boundary. And so that's what the value they use for each of these. Again, notice there's a distance of 20. So here's a class with the 20 still. Okay. And so here we can see there were 2 in the first class. So there's just a little bar there, 33 in the next. So it goes above 33. And you see this is kind of proportional, kind of a nice kind of way they do it, right? There's no gaps between the bars. They are all touching because there is no gaps in the data. Okay. Yeah, so this last part here is really kind of the biggest thing here. Histograms are usually generated using technology. That is something that is super true. We don't really do a lot of these things by hand once you get into actual applications because the data sets are just too large. For this class, I'll give you data sets that are less than 30 or so, and I'll make you do something like this, make you do one or the other, maybe both on a practice or something like that. But I typically don't make you do these by hand because it's just not practical. It's just tedious and doesn't teach you anything. Relative frequency histogram. Notice look here. I'm going to jump back to the last one where we had this. But jump back, it looks the exact same. The shape looks exactly the same. And even if we look at the x-axis, our horizontal axis, it's also the same. There. It's also the exact same. Okay. The difference is our vertical axis. Okay. Here it represents frequency. It goes 10, 20, 30, 40. Here it is percent, and it is 10, 20, 30, 40, 50, because our percentages go almost up to 50. So that is the only difference in these two graphs, whether it's relative frequency or frequency histogram, is the vertical axis. Okay. Everything else is pretty much the exact same. Okay. Just that vertical axis is what's different. So I'll let you guys read through this a little bit. Okay. When we're creating these graphs, we're not trying to tell a story. We're just trying to expose what the data says. Okay, so we don't want to try and make tricky graphs or anything like that, which is something we'll talk about towards the end of this lecture. Now, one of the things that we want to talk about when we talk about the graphs, this is why histograms are really nice, is it can give us an idea of the shape of the data. Okay. One of the most common shapes of data is a normal distribution, or is a bell shape. Okay, so it looks like a bell. In other words, right, bells kind of peak, kind of come down, a little flared base. And that is something that we call a normal distribution. A normal distribution has a bell shape. Okay, it's one of its key characteristics. All right. The frequency increases up to a max and then decreases. So frequencies go up to some sort of maximum high point, and then they come back down. And it has some symmetry. Now, nothing in the world is perfect, so it's not necessarily going to have exact perfect symmetry, but we want to have it kind of be similar. If we look back here, we can see that here we've got a little bit, then it kind of jumps and jumps up, but then we've got a little more, and then we've got a little bit. So this isn't quite bell-shaped. It kind of increases, then to a max, and then decreases, but the problem is it doesn't have that kind of symmetry. There's kind of this bump here. If this one here, let's say, was up here at a 33-ish range, 31, 32 for the frequency, or like in a 41% range, okay, then we might say it's a little more bell-shaped because it would kind of be a little more symmetric. But this one isn't, so we'll talk about that in a minute, what it is. Okay. So we just talked about this, right? A key characteristic of normal distribution, it has a bell shape, starts low, increases, symmetric. That's what I just said. So if we look here, we can see this kind of line right here. This is what's called a normal curve. And it's traced out over our data for this IQ group. And we can see that here we've got kind of this nice kind of, it fills in. Here it just drops off. It's kind of why it's not so much normal. No, it's not completely unnormal, but it's not exactly normal. So these questions that it's asking us here, right? What's its center? How much variation does the data have? Are there any outliers? These are things we're going to talk about how to calculate in later terms or in later classes. Now, if something is not normal shaped, but it is kind of bell shaped, such as the data we're dealing with, right? It lacks that kind of symmetry. We say that the data is skewed. Okay, so skewed data is something that's not symmetric. It still kind of has, it increases to a max, decreases down, kind of has that bell-ish shape, but it's not symmetric. We'd say the data is skewed. Okay, and there are two types of skewed. We have skewed right, skewed left. Okay, we say that data is skewed right if it has a longer right tail, and skewed left if it has a longer left tail. Now let's get some pictures and see what we mean by that. So we look at this data here. Okay, this we'll start with the green one. This green data here, this is pretty normal shaped. Okay, we can see it's got that nice little bell shape. It's pretty symmetric. We see that this kind of rises up smoothly and comes down smoothly, kind of ends about kind of similar distance away from the middle-ish. Okay, this is data that is approximately normally distributed. This one here, we can see that it has this kind of bellish shaped, but it's not symmetric. We see that this kind of goes up really quickly, but then this kind of goes down slowly. So this is the tail that it's talking about. So since this tail here goes off to the right, we would say that this data is skewed right. If we look over here, again, similar idea, right? This is kind of still has that bell shape, doesn't quite have that symmetry because this kind of has this long edge over here, or this long tail. Since this tail is off on the left-hand side, we say that this is skewed left. Now this data set here, this red one, it's not bell-shaped at all. This is not normal, and it's not skewed left or skewed right. This is something totally different that we will call a uniform distribution. It's approximately uniform or the same all the way across. Okay, and this is something that we'll talk more about later in the term into unit, I believe, unit 2. So those are some of the general shapes that we're going to see a lot in this class. Normal, uniform, skewed left, skewed right. Okay, make sure that you can kind of identify which ones are which. Now, here's a fun thing. Graphs that enlighten and graphs that deceive. Okay, so graphs of data are meant to inform us of the information in an unbiased, objective way. Okay. So some graphs are bad in the sense that contain like actual errors, but we also want to talk about misleading things that you can do to kind of trick up whoever's watching, whoever's looking at this data. Something that with an election coming up, we're definitely going to see. It's going to be really fun this term, being able to kind of relate these ideas to elections. One of the cool things with this class, for many of you, it's your last math class. And what's cool about this class is it has such great applications in the real world, both from a sense of you can find these things and calculate them in your work, but also when you see so many statistics come up in the news and in articles and things like that, it's really nice to have a better understanding of what they're representing so you can be a more informed consumer. So, scatter plots, when we typically have a kind of a relationship that we're trying to look at, see if two things are possibly correlated, right? If you remember from the first class, right? Causation and correlation, big deals, right? Just because two things are correlated or kind of happen to be at the same time doesn't mean they are causal, right? And here we can see that the relationship between waist circumference in centimeters and arm circumference in centimeters appears to have a correlation, or in other words, as one gets bigger, so does the other. So they're kind of related to each other. Okay, that does not mean that waist circumference causes larger waist circumferences cause a larger arm circumference. It just means that they're related. This is a time series graph, so these are just kind of the changing of things over time, right? Most of these aren't things we're going to do. We're going to stick with frequency tables, relative frequency tables, and histograms in this class, but these are good things to know. Dot plots, something similar to, you may have heard them as stem and leaf plots, are kind of a similar idea. Each dot on top of each other represents just kind of multiple frequencies, so we can see that right here, this had 2 occurrences, this had 1, this had 4. And so that kind of is very similar to kind of a histogram kind of makeup, about dots instead of bars. Here's that stem and leaf plot that I was talking about. Bar graphs. So bar graphs are different than histograms in that they have gaps between their bars. You can kind of overlay different bar graphs on top of each other. They can be really good. They can also be kind of misleading. So here we can see that this is a multiple bar graph on medium income by gender, okay, based on year, and then their income in thousands of dollars. You see that blue is male, pink is female, and so we can see kind of as time has gone on, male's income has gone up, as has female income, but the disproportionality between the two of them is still excessive in my mind. So pie charts, this is what I'm talking about. So when we have kind of categorical data or qualitative data, that pie charts are things that are really good to do. A lot of the times what they'll also include in these are percentages. So they'll include kind of what percent of respondents answered family or partner to whatever question it is they were asked. Now, graphs that deceive, this is where it gets fun. Okay, the first thing is a non-zero axis. So what that means is basically starting at a point other than 0. So you're not showing the entire data, you're just showing a part of the data. And we can see this graph on the left is meant to deceive us. It's meant to make us think, if we look at what it tells us, it's highway fuel consumption in miles per gallon. If we look at this, we're meant to see, oh man, the Honda Civic is really good and the Camry is kind of crappy, right? Look at that. That's a huge gap. But when we restart our scale at 0, we can see that we're all pretty good, right? Because when we look at this, instantly we go, wow. We may not jump over here and see, oh, this is 31, this is 36. So there's 5 miles per gallon different, which is kind of fun, it's kind of significant, but it's not necessarily practically significant, right? If that is the only thing that's difference between the two, sure, maybe you take a Honda, but I think there's more differences between a Honda Civic and a Toyota Camry than that 5 miles. Three-dimensional objects. They can be kind of confusing. Okay. Here we can see money. It's kind of blurry. It doesn't really make sense. So this is kind of a bad idea. The data is nice that it gives us that, but ultimately the picture is kind of deceptive in kind of how accurately it represents things, especially with this kind of white space here in the image they chose. This is the same information as here. Okay. Now, what exactly is it that you're looking at that you're supposed to compare? Because the difference from having a bachelor's degree to an advanced degree is a little over $13,000. But this box looks significantly larger than this one. These boxes are cubes, so their height, width, and kind of length are all the same. But what these numbers correspond to is simply the height of the box. So while this box's height is only about 13,000 bigger, it also increased its width by that much and its length by that much. So it made that box look significantly larger. And so using kind of odd images and things like that may be fun and catch the eye, but it is kind of something that can be very misleading to the information. What is it that you're supposed to be looking at with this table? I definitely know for firsthand experience, but a lot of people will look at a picture or a video far before they look to the words describing what's going on. So even though someone may have these pictures and may have a very clear, accurate description of what's going on inside, people aren't reading that. So here is a nice, fair, objective, unencumbered by distracting features look at this information. So this is simply annual income averages based on education level. So all three of these are the same information. We can see here that it's pretty clear kind of what is happening with the information. Again, we've got these bars. These numbers on top are not required, but it is really nice. It kind of gives you an exact value clearly what's going on. So if you're creating anything, make sure you guys are keeping an eye on kind of what you're doing. Now, if this is something that's really interesting to you, you're like, man, that's really kind of crazy. Like the same exact data is looked at 3 different ways, and each one kind of can show a different picture, right? If I was, say, running a graduate program and I wanted students to come take my program because I'm like, you can make more money, I'd want to show this because this makes it look like having an advanced degree or a graduate degree significantly more than just a bachelor's. But if I want them to kind of all look the same, like this doesn't look too far off. Like these kind of look like, yeah, it's not too bad. But then this is a really accurate representation. So kind of what you're wanting to show with the data is very kind of telling as well. If this is something that interests you, there's a really fun book out there written in like the 50s or 60s about how to lie with statistics. It's super consistent, super accurate, even still today. So if you're really bored in all this free time that you've got with the coronavirus keeping us locked down, look up that book and give it a read. It's pretty short. All right, you guys, that's it for week 2. Hope you guys understood that, learned something, and go after the quiz or the video questions and then get on the homework. All right, you guys, see you next week.